A radio signal, unlike anything detected before, has just emerged from the direction of Proxima Centauri, the closest star to our own, just 4.2 light-years away. For scientists, this isn't just static. It's a potential message that could confirm intelligent life is hiding right next door. If this anomaly is real, everything we know about our place in the universe could change overnight. But is this strange broadcast a cosmic invitation or a warning written in code? The answer may determine whether we are truly alone and what happens when we listen. Proxima Centauri sits just 4.2 light-years from us, a cosmic stone's throw. That distance sounds abstract, but in the language of space, it's next door. Light, moving at nearly 300,000 kilometers each second, takes over 4 years to bridge the gap. If you could drive there at highway speed, it would take more than 50 million years to arrive. Even so, Proxima is the closest star to our Sun, part of the Alpha Centauri triple system. It glows faintly red, much dimmer than the Sun, invisible to the naked eye. Yet, in astronomical terms, it's practically within reach. The gap between Earth and Proxima Centauri is about 40 trillion kilometers, 40,000 billion. For comparison, the farthest human-made object, Voyager 1, has only traveled about 0.002 light-years since 1977. That's less than 1/20% of the way to Proxima. Despite the gulf, this neighbor star has become a focal point for astronomers, not because of its brightness or size, but because it's the nearest possible place, outside our solar system, where something extraordinary could happen. When a signal appears to come from that direction, the numbers suddenly feel smaller, the silence between stars less absolute. Proxima is close enough to make the question real. What, or who, might be waiting just across the interstellar divide? Proxima Centauri isn't just close, it has a world that's captured imagination since 2016. That planet is Proxima B. Astronomers confirmed it orbits its dim red sun every 11 days, far tighter than Mercury hugs ours. Yet, by a cosmic quirk, Proxima B sits in the so-called habitable zone, the region where temperatures could, in theory, allow liquid water to pool on its surface. Not too hot, not too cold. The kind of place, at least on paper, where life could try to gain a foothold. But life's odds here are anything but simple. Proxima Centauri is an M-class red dwarf, cooler and fainter than the Sun, but far more volatile. Flares erupt with brutal regularity, blanketing Proxima B in ultraviolet and X-ray storms. Some bursts are so intense they dwarf the largest solar flares ever recorded on Earth. Models suggest that, unless Proxima B began with an atmosphere hundreds of times thicker than ours, most of its air and water may have been blasted away in the star's wild youth. If the planet doesn't have a powerful magnetic field, those flares could strip away what little protection remains. Even so, there are possibilities. If Proxima B managed to hold onto a dense atmosphere, maybe through volcanic outgassing or sheer luck, then heat could flow from its perpetual day side to the night, softening the extremes. Along the twilight band, where day meets night, conditions might hover near the freezing point. There, in the endless dusk, water could stay liquid. Life, if it exists, would have to be tough, resilient, and perhaps nothing like what we know. Still, for scientists searching for signals, Proxima B is the nearest place where the old question, "Are we alone?" feels less like fantasy and more like a challenge waiting for an answer. In the summer of 1977, a single printout from Ohio State's Big Ear radio telescope changed the tone of the search for life in the universe. The data looked routine, columns of numbers, a stream of radio static logged at 1,420 megahertz, the natural frequency of hydrogen. But then, for exactly 72 seconds, the telescope recorded a spike so sharp and so clean, it seemed to leap out of the cosmic noise. Jerry Amon, the astronomer on duty, circled the burst in red pen and scribbled a single word in the margin. Wow. That annotation became legend. The wow signal didn't repeat. It didn't match any known satellite or terrestrial source. For decades, it stood as the closest thing to a cosmic handshake, brief, unexplained, and forever out of reach. No one could say where it came from, or whether it was a fluke of nature, a stray earthly broadcast, or something crafted with intent. The Big Ear's analog systems offered little to go on. No precise coordinates, no detailed spectrum, just a spike and a mystery. The world changed in the wake of that 72-second anomaly. The scientific community launched new projects, built bigger dishes, and began dreaming of a day when technology could catch a signal and pin down its source. But for all their advances, the core question lingered. Was the WOW signal a false alarm, or the first whisper from another world? The tools of the 1970s could only go so far. Tape reels and paper printouts captured the moment, but not the full story. Each new generation of astronomers returned to that red-circled printout, searching for patterns, for echoes, for anything that might turn a one-off into a conversation. The legacy of that moment is not just a mystery, but a challenge, a dare to listen harder and look deeper, in hopes that the next anomaly will leave more than just a question mark in its wake. By the mid-2010s, the search for signals from other worlds had outgrown its roots in static-laden printouts and late-night hunches. In 2015, Breakthrough Listen launched with a single goal: sweep the sky for techno-signatures using every tool modern science could muster. The project poured millions into upgrades for telescopes like Parkes in Australia and Green Bank in the US, and, more importantly, into a new breed of search strategies. Gone were the days of waiting for a lucky spike on an analog chart. Now, teams programmed algorithms to sift through millions of radio channels at once, flagging the rarest patterns and filtering out the relentless background of earthly chatter. One technique became central: the on-off cadence. Observers would point the dish at a target, say Proxima Centauri, for several minutes, then swing to a nearby patch of empty sky. If a signal appeared only when the telescope stared at the star and vanished when it looked away, that was a clue. Not proof, but enough to demand closer scrutiny. This rhythmic toggling, almost like a heartbeat, helped separate the cosmic from the local. It was a lesson learned from decades of false alarms and near misses, now baked into the digital bones of every major SETI campaign. But the real leap wasn't just in hardware or clever routines. Breakthrough Listen's software could process petabytes of data, running custom algorithms that learned to spot the signature of a drifting, narrowband carrier, a hallmark of artificial transmission. The system didn't just look for loud spikes. It hunted for subtle, persistent signals that might slip past human eyes. Each candidate was cross-checked against vast catalogs of satellites, radar, and local interference, then scored by likelihood. Most were tossed aside in seconds. A handful survived for deeper analysis. Out of billions of possibilities, only the most stubborn anomalies made it through the net. The modern SETI effort is less a fishing trip and more a digital trawl, relentless, methodical, and always refining its catch. The hope is simple: if something out there is sending, these tools are sharp enough to notice, even if it's only a whisper in the cosmic static. April 29, 2019. Parkes Observatory in Australia is locked onto Proxima Centauri, its 64-meter dish drinking in radio waves from the southern sky. The Breakthrough Listen team is running a campaign, 30-minute blocks pointed at Proxima, broken up by short 5-minute scans of empty sky. The goal is simple: catch anything that stands out from the cosmic background, then see if it disappears when the telescope looks away. A spike appears at 982.002 MHz. This isn't just any radio noise. The carrier is ultra-narrow, packed into less than a single hertz, far sharper than what nature usually produces. The signal persists for over 2 hours, flickering in and out only as the telescope's gaze shifts. Every time the dish aims at Proxima, the line reappears. Every time it moves off, the line vanishes. The cadence is relentless. On, off, on, off. Each switch is logged with precise timestamps, frequency bins, and pointing coordinates. The team's algorithms flag the event as a candidate, ranking it among millions of other blips, but this one refuses to fade into the noise. The raw data is poured into waterfall spectrograms, time on one axis, frequency on the other. The result is a razor-thin streak, drifting slightly across the band, but never losing its shape. That drift, measured in just a few tenths of a hertz per second, doesn't match any known satellite, nor does it fit the expected Doppler shift from Earth's rotation or Proxima's motion. The bandwidth is so tight, so precise, that it looks engineered, not accidental. For comparison, even the sharpest natural masers in space are thousands of times wider. Here, the signal is almost surgical. Across more than 2 hours of data, the pattern repeats. Only on source, only at 982 megahertz, only when the telescope's eye is fixed on the closest star. The team checks the logs. No immediate hardware faults, no catalog transmitters. The frequency sits in a quiet part of the spectrum, far from the usual suspects. In the world of SETI, this is as close to a bullseye as the data can offer, at least on the surface. The numbers are clear. The mystery, for now, is absolute. BLC-1 wasn't just a solitary spike. When Breakthrough Listen's analysts stretched the data, something stranger came into focus. The signal didn't sit still. Its frequency shifted, drifting by fractions of a hertz every second, tracing a slow, deliberate path across the spectrum. In radio astronomy, drift is a fingerprint. Earth's rotation, a planet's motion, even a transmitter's speed, all leave their mark. But BLC-1's drift didn't fit any of the usual suspects. It didn't line up with the Doppler shift from Earth's spin or Proxima's orbit. It was out of sync with every satellite and known transmitter. For a moment, it looked like a genuine anomaly, a signal that refused to play by terrestrial rules. Then came the real head-scratcher. As the team combed through the waterfall plots, they found not just one, but dozens of ultra-narrow lines. Each sat at a different frequency, yet all were spaced out in a neat, regular pattern, exactly 2 megahertz apart. These were BLC-1's spectral cousins, each drifting in lockstep with the original. Some were faint, barely peaking above the noise. Others flared up, then faded, as if echoing a hidden clock deep inside the system. None appeared when the telescope looked away from Proxima. Every single one obeyed the on-off cadence. To radio engineers, a pattern like this whispers of something mechanical. Intermodulation, when two signals mix inside a receiver, can spawn a whole family of copycat lines, each spaced by the beat of an internal oscillator. Parkes' own down converter boards, packed with digital clocks and oscillators, became the prime suspects. Lab tests showed that under certain conditions, a strong radio spike, mixed with the right clock frequency, could produce a parade of look-alike signals, all drifting together, all tied to the same electronic heartbeat. But there was a catch. The lab artifacts never matched BLC-1's drift exactly. Close, but not perfect. The mystery deepened. Was this a cosmic call, or a ghost in the machine, clever enough to fool even the sharpest eyes? The evidence piled up, but the verdict stayed out of reach. Every new clue pointed in a different direction. For scientists, this was the moment when excitement curdled into doubt, when the line between discovery and deception blurred, and every answer only raised more questions. Inside the Breakthrough Listen lab, the atmosphere thickened with each new alert. Slack channels pinged at all hours, messages stacking up faster than anyone could answer. Sophia Sheikh, the lead analyst, barely left her desk for 3 days. Coffee cups multiplied. Screens glowed with waterfall plots, thin, drifting lines that refused to match any known satellite or local transmitter. Every log entry from April 29th was double-checked, then triple-checked. Raw data drives were swapped and sealed, just in case. The team's group chat scrolled by in a blur. Questions, hunches, frantic calculations. No one slept well. Some didn't sleep at all. Emergency algorithm reruns ran through the night, searching for a pattern or a flaw. One by one, the usual suspects were crossed off the list. The 982 megahertz spike kept reappearing, only when the telescope stared at Proxima. Each time the signal flickered back into view, hope surged, then crashed against a new wave of doubt. Was this a cosmic transmission, or just a clever trick of the electronics? Sheikh's notebook filled with scribbled times and frequencies. At 2 a.m., she called for a fresh set of cross-checks, pulling in colleagues from Green Bank and Berkeley. The pressure was relentless. For 72 hours, the lab ran on adrenaline and raw curiosity. The cost was measured in missed meals, bleary eyes, and the gnawing sense that any mistake could mean missing the biggest discovery in SETI's history, or chasing a ghost. In those hours, the data was more than numbers. It was a question that refused to let anyone rest. December 2020. The BLC-1 signal leaves the confines of Slack channels and lab notebooks, spilling into a global spectacle. News outlets push headlines hinting at first contact. For a brief window, the world's attention swings to a faint radio pulse from the nearest star. The Breakthrough Listen team fields interview requests, their inboxes flooded with questions that science can't yet answer. In online forums, the debate turns feverish. Some see the signal as a cosmic invitation. Others warn of wishful thinking, echoing decades of false alarms. Avi Loeb, Harvard astrophysicist and outspoken advocate for open-mindedness, enters the fray. He argues that BLC-1 deserves the same scrutiny as Oumuamua, the interstellar object that, in 2017, he controversially suggested might be artificial. Loeb tells reporters that extraordinary claims demand extraordinary evidence, but also extraordinary courage. He points to the history of missed opportunities, urging scientists not to dismiss anomalies just because they're rare or unsettling. His words fan the flames, drawing both supporters and critics. On the other side, Seth Shostak of the SETI Institute urges restraint. He cautions against what he calls techno-signature tourism, seeing aliens in every unexplained blip. Shostak reminds the public that most signals, even the most tantalizing, end up with mundane explanations. He calls for patience, for more data, for skepticism sharpened by experience. The two voices, Loeb's optimism and Shostak's caution, set the tone for a debate that stretches far beyond academia. Social media swells with speculation. Talk shows and podcasts revisit the old question: if we do receive a message, should we answer? Some invoke the so-called dark forest scenario, warning that announcing our presence could be dangerous. The ethics of cosmic contact become dinner-table conversation. In the background, the shadow of 3I Atlas, another interstellar mystery, lurks as a reminder that the universe is full of anomalies we barely understand. For a moment, the world stands at the edge of a new kind of uncertainty, caught between hope, fear, and the unknown. In April 2019, the Parkes Murayang telescope captured BLC-1, a 982 MHz signal lasting over 2 hours, detectable only when pointed at Proxima Centauri. The Breakthrough Listen team applied rigorous on-source and off-source methods, ruling out most known sources of terrestrial interference. Yet, like the 1977 WOW signal, BLC-1 was never repeated, and its origin remains uncertain. Documents from the December 2020 summit show scientists divided. Some cite unexplained frequency drift and on-target persistence, while others highlight equipment artifacts. To date, no evidence confirms the signal as artificial, but no definitive cause has been found either. The release of all data and methods has enabled worldwide scrutiny. As new observatories like the Rubin and JWST prepare to scan the cosmos, scientists expect more unexplained signals ahead. The BLC-1 case shows that even with advanced tools, some cosmic mysteries persist. This was not the first unexplained message, and by the data, it will not be the last.